In this Mathematica Sessions episode number 7 of Discrete Math, we're going to be looking at functions in more detail than the last episode, and in particular, composition of functions, whether functions are one-to-one and onto, in other words, surjective, injective, actually the other way around, and bijective. Okay, so if you're interested in that, keep watching. And we have a problem set mainly on functions. So what we're doing in this problem set is learning about functions, the composition of functions, and the concepts of one-to-one and onto and bijections. All right, and if you have the tool of bijections at your fingertips, then you are able to prove that two sets can have the same cardinality because you're able to prove that there's a bijection from one to another. Okay, so that's an overview of what we'll do. Now let's begin with the first problem, and that says define a function f mapping the rational numbers to the integers by f of x is equal to twice the floor of x plus 1 for all x belonging to the rational numbers. And then we've got some questions, but I'll just point out, here I've got the set notation for the set of integers, but I don't have that at my fingertips for the rational numbers, and so I'll just use two Q's next to each other to mean rational numbers. Okay, so is f one-to-one? Prove or disprove? Okay, so what we want to do here is basically assume that f of x1 is equal to f of x2, and then we have to show that x1 equals x2, right? So let's just set this out as a general technique. So to prove something is one-to-one, and I'll use this as shorthand to mean one-to-one, the technique we do is basically assume f of x1 is equal to f of x2, and what we do is prove that x1 is equal to x2. So that's the general technique that we use to prove that a function f is one-to-one. All right, but in this case, you can notice, because of what this function does, right? It sends x plus 1 to the greatest integer less than or equal to it. So you can imagine quite easily that two x values can end up in the same at the same y value. Okay, so basically we're going to disprove this because it's quite clear that it's not one-to-one. Okay, so we'll say no, not one-to-one. Okay, and the reason why is because, for example, f of 0 is equal to 2 times the floor of 0 plus 1. Okay, so twice the floor of 1, and the floor of 1 is 1, so this is 2, right? However, on the other hand, f of 1/4 is twice the floor of 1/4 plus 1. Okay, and then the floor of 1 and 1/4, or 1.25, is equal to 1. So this is twice the floor of 1.25, and so this is just 2 times 1, which is 2. So we see here that f of 0 is equal to f of 1/4. So f of 0 is equal to f of 1/4, but 0 is not equal to 1/4. Hence, not 1-to-1. Okay, any questions about that? All right, I'll turn this into a comment. And then we'll have a look at the next one. So the next one says, is f onto? Now the question we need to ask for this problem is, does every element in the codomain over here, does every element in this set, integers, does it come from somewhere? Okay, so let's just write this. Does every x in this set come from some element of the rationals under the map F? All right. Now, to answer that question, you just look at what comes out of this, right? So the output of this is twice an integer, because the floor of a number is always an integer. So let's just say then, since f of x is twice this, comma, so twice an integer. In other words, range is the even numbers. So write the even numbers as 2z. Odd numbers don't have an x from which they came, right? Okay, so there is no x belonging to the rational numbers such that f of x is equal to, say, 3, right? Because 3 is an odd number, and the output of this function is the set of even numbers. Okay, so we conclude f is not onto. Right, and we'll turn this into a comment. And then I'll press save. All right, any questions about that one? Okay, so next one, what is the range of f? Well, we already know this, right? I've written it right there. So the range is twice the set of integers, or the set of even integers. So we'll just say range is 2z, okay, but it says give it as a set. That's a set, but let's be sure that we can write this in a proper way. Okay, so I'll pull up the palette and I'll get my belonging to symbol. Should be in here. All right, so the set of all x belonging to the integers such that x is equal to 2 times y, where y is an integer. Okay, now that's a bit overkill, but sure, we've done it with the set notation brackets. Okay, but I mean, I would think that 2z is descriptive enough. All right, so let's have a look at the fourth one in this question 8.1, which says define g maps integers to integers by g of x is 2x minus 1. Okay, so what comes out of this is the set of odd numbers, right? For all x belonging to the integers, determine the composed map g circ f of x, right? And I've got the definition here, and that's not in your problem sheet, but that helps, right? That this is defined to be g of f of x. Okay, and calculate then what is the composed function at minus 3/4. Okay, so we'll just take this part right here because we have to find this first. And so this is g of, what is f of x? Hang on. Why do I have not have f? Oh, it's up here, isn't it? Okay, f is this one. So I just want this part of it. Great. So it's g of twice the floor of x plus 1. Okay, and now we simplify. So the function says multiply by 2 and then subtract 1. So it's 2 times, in brackets, something minus 1, but that something comes from the inside here. So we take it and we sub it in there. Okay, now simplify, and we have 4 times the floor of x plus 1 and then minus 1. Okay, so we've got the description of the function. And so let's just reiterate. It sends x to 4 times the floor of x plus 1 and then minus 1. Okay, good. Now that we have that, we can calculate what it does to minus 3/4. So copy this, and then we'll replace the x with minus 3/4. Okay, and now we want to simplify this. So we have 4 times the floor of 1/4, isn't it? 1 minus 3 is 1. Or sorry, 4 minus 3 is 1, so we've got 1/4 there. Okay, and simplifying that, the floor of 1/4 is 0. So then we have 4 times 0, then subtract 1, and this is minus 1. Okay, good. So we've completed that part of the exercise. All right, so the next part says, what is the range of this function here? So that's this one here. What is the range of that? Okay, so let's just copy down the description of it. So we have this description, 4 times this integer minus 1, but what comes out of this essentially are the set of, I mean, you look at the 4 here, right? So if you look at remainders mod 4, the remainder of this mod 4 is 3, right? So let's write then that the range of this function is equal to the set of all, let's just say integers y. Okay, so y belonging to z, such that y is congruent. What do I want the congruent symbol? Sure, I'll just use that. Okay, congruent to 3, and then we want to say modulo 4. Okay, so it's the set of all integers congruent to 3 mod 4. You could equally say the set of all integers congruent to minus 1 mod 4 as well, and that would be perfectly fine. Okay, let's make that a comment. And this as well. And we'll have a look at the next problem, which is 8.2. How are we going, guys? You following along okay? Still with me? Good, thanks, Jeremy. Of course, if you have any questions, just let me know, either verbally or in the chat, however you feel comfortable. Okay, so 8.2 says, let f map integers to integers by f of x is x cubed minus 1. And then we've got a function g of x sends integers to integers, and that should say g of x. G of x is equal to x plus 5. Okay, so write each of f compose g and g compose f, as a polynomial. Okay, so let's begin with this one. So what we want is f compose g of x, and now let's just use the definition of that. That is f of g of x. Okay, and so we sub in g of x first. So we have f of g of x right here. And then we simplify that. So remember what this does, f cubes and then subtract 1, except I want to put the bracket here because I want to sub in where the x was, I want x plus 5. Okay, great. So now it says write it as a polynomial. Obviously, this is always already a polynomial, but let's expand that just so that we get the coefficients of each of the powers of x, all right? So what I'm going to do is I'm just going to use some code here to expand that. And since I'm in software Mathematica, I can just do that rather easily. And here we see this, the problem is it puts it backwards, but that's okay, all right? So now we can come up here and write that it's this. And hey, why don't we just reverse it manually here? So it looks nice. Okay, and then we've got plus 75x. And then plus 124. All right, good. So we've done that job. Space it out so that it's easy to look at. Okay, now next we need to do the other way around. So G compose F. Put this in a comment too, because I might end up expanding something. Okay, so this is G of F of X, right? And so I take F of X here, which is X cubed minus 1. I've got to apply G to that. Okay, now what G does is it takes something and it adds 5, right? Now the something comes from this, what's inside the brackets. So I'll take that and I'll put it there. And now I just want to expand that, but of course you can do that easily in your head. So what we have here is x cubed minus 1 plus 5, and that's x cubed plus 4. Okay, great. So we've done that part. Okay, so let's have a look at the next question. Which of these is a bijection? So in other words, which of these is both one-to-one and onto? All right, so let's start with F. Okay, so F is one-to-one. F is one-to-one, but not onto. Okay, so let's just go through the details of that. So which is F again? F is this right here, right? So just copy that here. Actually, you know what? Let's just copy them right here so that they're all that are where we can see them. So this is G right here. Okay, and then we also need G composed F. Now that was this one. G compose F equal to this, and it also sends integers to integers. All right, so now that we have all those, so F is one-to-one, but not onto, and so I'll just go through the details of proving that F is one-to-one. So, in other words, assume F of X is equal to F of, say, Y. Okay, then what we have is that X cubed minus 1 is equal to Y cubed minus 1. Okay, now let's simplify that. So what we have then is that x cubed is equal to y cubed because we can add 1 to both sides. But the way we want to express this is x cubed minus y cubed is 0. Okay, so express it like that and then factorize the left-hand side of this. All right, so I'll turn this into a comment so I can just use the computer to help, but it should be probably in most of your memories what that factorization is. All right, so yeah, I'll just write it here. Factor this difference. Okay, and so here we see what the factorization of the difference is. Right, so what we have then is that so that this is equal to 0. All right, now you're not done at this point in proving that it's 1-to-1, because what you have to do next is consider the domain, right? So the domain here is the set of integers, right? But in fact, this part right here is never 0, right? So let's just how do I demonstrate this? So basically, if you try to solve for x here, okay, and I'll just use the computer to demonstrate this. So in other words, what I'm going to say is solve this quadratic equation equal to 0 for x, right? And so you see that to do that, you've got to introduce complex numbers. All right, so in other words, this one is never 0. So we'll say, but this is not equal to 0 for x belonging to the integers. Okay, and so say hence x minus y is equal to 0, so x is equal to y. All right, we have shown that f is 1-to-1. Okay, so f's 1-to-1, but it's not onto. So f is not onto. Okay, and we'll take an example. There is no x such that f of x is equal to 1. Okay, so let's just demonstrate that in more detail. So assume f of x is equal to 1. Right, then what that means is x cubed minus 1 is equal to 1, right? So what we have is that x cubed is equal to 2. Right, now we take the cube root of this, and we see that it's not an integer, right? So the cube root, and there are 3 cube roots, right? So to show you this, I'm just going to use the computer again. Right, this time I'm going to go for a numerical solution, so I'll just write nsolve here in Mathematica. Nsolve this equal to 2 for x. Okay, so you see the numerical solutions here, and you quickly see none of these are integers, right? So no, none are integer. Hence, what we get is that f is not onto. Shift this a little bit over so you can see, and I need to open my window. There's a strange smell around. I don't think it's me. But anyway, I want fresh air. You guys still hear me okay? Yep, good. Thanks, Jeremy. All right, any questions? All right, so now we're not done. I mean, I've gone into perhaps too many details there on why f is 1-to-1 but not onto. Now, you could do the same for g. All right, so remember what g is. So I'll copy this again. And Maybe I even want to go into a new cell, but nah, it's okay. I'll just put it here. Okay, so remember G. All right, so this is the description of G, but you can clearly see that G is 1-to-1 because if G of X is equal to G of Y, then clearly X is equal to Y. So G is 1-to-1. G is also onto and onto. All right, and so the way you do that to show onto, so we say assume that Y is in the set of on the right hand side, so this one, which is just integers. Okay, assume Y in Z satisfies Y is equal to, let's see, X plus 5. Now we solve this for X. Solve for X. And what we have then is that X is equal to Y minus 5, all right? So in other words, what I'm doing is I'm finding the inverse, and that also shows you that the function is onto. Okay, now the next part is what the inverse map is. So G inverse of X sends X to X minus 5. All right, so that tells you that it's onto because you can always go back, right? And now, but what you need to notice is that this belongs to the set on the left-hand side. So this is in this set here. Okay, good. Now, G compose F. So actually, we need to finish this off. So G is both 1-to-1 and onto, so G is a bijection. Okay, and now that we've got that, let's look at this map. All right, so this map, it is also 1-to-1, right? So this is 1-to-1 for the same reason. I mean, we can say, assume that this map of X is equal to the same map of Y, and then we again deduce that X cubed is equal to Y cubed, and for the same reason as F was 1-to-1, this one is 1-to-1. Okay, so I won't write that. I assume you can just follow what we've done already and do that yourself. Now, it's not, but not onto. So basically, 0 does not come from some X in the set of integers. So this one on the left here. All right, and let's just look at that claim in more detail, right? So if f of x, which is x cubed plus 4, is equal to 0, then can we find an x in the set of integers such that it maps to 0? Then we have x cubed is minus 4. But the three roots, the three complex roots, I want to say of the three roots, of the, not the of the three roots, none are integers. Okay, hence this map is not onto. It's not onto, not surjective. Surjective is another word for onto. Injective is another word for 1-to-1. Okay, great. So we've got that. All right, Jeremy's got a question. For proving the function is not onto, can it be done just by finding a counterexample? Yeah, that's right, Jeremy. So you've got to find an element in the codomain, that is the set on the right-hand side of the description of the map, and just show that some number in this set didn't come from somewhere, right? And so to do that, and you can see what I've done here. I've done exactly that, right? I've chosen an element in this codomain and shown that it doesn't come from somewhere. And so that is a counterexample. Yeah, so you're saying a little bit more. So not necessary to prove it by definition in assessment and exam. Well, no, that's perfectly fine. This is perfectly fine for the assessment and the exam to show that it's not onto. Is to prove it, give a counterexample, right? Because a counterexample is a disproof of some claim. Okay, good. All right, thanks, Jeremy, for the question. All right, so let's move on to the next one. Let's see, what have we done here? We've done part B, so I guess we're on to 8 point. Oh, hang on. All right, so we've got more. Part C. For each bijection in B, determine the inverse. Okay. So we've already done this, I think, for G. All right, so I'll just state it. G inverse of X is equal to X minus 5. And I think we stated that above, or worked out how to do that above in the process of showing that it was onto. Okay, yeah, and so that's the only bijection of the above, and so that's that part complete. Okay, good. Now this one could be a bit of a pain here. Repeat B and C with F defined on the real numbers, sending real numbers to real numbers, and G sending real numbers to real numbers. Okay, so basically, I mean, the rules are the same, right? So let's go up and copy those rules. If I can find them here. These are the rules, except they map from real numbers to real numbers. So just copy and paste this, real to real. Okay, so now we've got these maps. And what B and C said again, are they bijections? Okay, so in this case, yes, all of those should be bijections, right? Now the tricky part comes in that you'll find that you have 3 roots of you know, x cubed equals some number, right? But you'll always be able to find one cube root. So one real cube root, I hope I said. Okay, so let's write this under here. Okay, so F is 1 to 1. Since we can always find at least one real cube root of a real number. Okay, it's also, F is also onto. It's also surjective, right? Because, oh, hang on. No, I've got this wrong. I've got this the wrong way around. This should have been onto here. F is onto, since we can always find at least one real cube root of cube root of a real number. Okay, F is also 1 to 1 for same reasons as above. We've already done that for integers going to integers, and so that part doesn't change. Okay, good. So F is a bijection in this case. All right, now G was a bijection before, and so G is still a bijection when we change the sets. Right now, with G compose F, this one is one-to-one, as it was before. One-to-one as it was earlier, but now is also onto, right? Because we're solving this equals y for x. What we get is x cubed is equal to y minus 4. And so we can take a cube root, right? We can find a real cube root of y minus 4. Okay, so it is onto also. Hence, this is a bijection. Right, so in other words, all of these are bijections, right? And so the next part of the question is find the inverse maps of each of these. Okay, so to do that, I need to go open the palette and find the cube root button. So I'll just put that right here. And we need to put a 3 there. And so this one here, x plus 1, will be the inverse of f. So f inverse of x is the cube root of x plus 1. And then likewise, g compose f inverted will look similar. Right, but this one is x minus 4 inside the cube root. Okay, now g inverse is really simple. So g inverse of x, we've already written this. It's the same as it was before, so it's just x minus 5. Okay, great. Any questions about this? All right, looking good. So I'll turn this into a comment and we'll carry on. Save this while I'm at it. Okay, great. That brings us to the next question, which is 8.3. Let f and g be functions. Prove or disprove the following. If both f and f compose g are one-to-one, then g is one-to-one. All right, so with this one, we want to proceed by proof by contradiction. Okay, so what we have here is proposition P implies proposition Q, right? We're going to prove this by contradiction. And that would be to assume that we have a T implies F case, right? Because that's the only one in which an implication is false. Okay, so let's set this up. Okay, so what we're doing then is assuming that the premise is true. So assume both F and F compose G are one-to-one maps or functions. But while G is not one-to-one, I'll put this in capital, so not one-to-one. Okay, so under this assumption then there exists, say, an x and a y, such that g of x is equal to g of y and x not equal to y. Okay, so in other words, these are distinct. Okay, so, but still, since we've assumed that f and g F composed G are 1 to 1, we'll soon run into a contradiction, hopefully, right? All right, so since F is 1 to 1, so since F is 1 to 1, F of this number here, right, G of X, is equal to F of the same number. Remember, these are the same. This is the same number here. G of X is the same as G of Y. So all I'm doing is writing F of something twice, right? The same something. All right. So this is what we have, right? Meaning that F compose G of X is equal to F compose G of Y. Okay, so this is what we've deduced. F compose G of X is equal to F compose G of Y, but X is not equal to Y. Okay, and so this says that so F compose G is not 1 to 1. However, this is a contradiction, right? Because we assumed that it is 1 to 1. And whoops, I shouldn't have pressed that button because it did, it converted this into Wolfram alpha. And so now I get an error message. So this is why I make everything a comment here. I mostly use this to type in, right, Mathematica, but it's occasionally useful to do some calculations here as well. And of course, there are downsides, and one of those is that when I'm typing I accidentally turn things into Wolfram alpha script. All right. So so this completes the proof, and so we'll say, right, since we obtained that contradiction, hence we have proved the result. All right, great. So now let's look at the next one, unless you have any questions about that. Okay, so same story, F and G are functions, prove or disprove. So we're doing this one now. Both of these are onto, if both of those are onto, then G is onto. Okay, so this one's false, right? And you've got to play around a little bit before you realize exactly why. But so I'll just show you some very simple sets that show you why this is false. Okay, so let's just say false. And we're giving a reason why. So define some maps and some sets, right? So G sends the set containing the number 1, 2, the set containing 2 and 3, and explicitly by G of 1 equals 2. Okay, so now you can see that 3 didn't come from somewhere, right? So this is defined for all the elements in the set X on the left, right? It's a function, but it's not onto. So notice G is not onto because since 3 did not come from some element of the set containing 1 under the map G. Okay, so it's not onto. All right, now next we want to define a map F. So now define F sends the set 2, 3 to the set containing 4 by f of 2 is equal to 4 and f of 3 is also equal to 4. Okay, now this set here, this is onto, right? Is onto, since every element in the set containing 4. So 4 came from some element of the set containing 2 and 3. Okay, now let's consider the composed map. So F compose G. All right, so this is a rule that sends, because G is on the right-hand side here, so it sends this set 1, and now the ultimate destination here is the set 4. So it sends the set containing 1 to the set containing 4, and let's look at the explicit rule by F compose G of. Now there's only one element in the set 1, right? So this will be the full description of the map. So F compose G of 1 is equal to 4, right? Okay, so this function is onto, right? So 4 came from somewhere, right? So what we have here is that, so both of these are onto, but G is not onto. So in other words, we have T implies F is false, right? So this is a counterexample. Any questions about that? All right, great. So we'll turn this into a comment and we'll move on to have a look at the next one. I think should be 8.4. All right, 8.4, find a one-to-one function f mapping this set to this set. Now I'll just define these sets for you. So Z with a superscript of plus. So that suggests, and you don't always have to write it that way, but it suggests we're talking about the positive integers. So we'll assume this means positive integers. Now this notation is somewhat more ambiguous, so you've got to rely on the context here. But in this case, so this means, in this case, it means 3 copies of this. So the Cartesian product. So this, and then we'll just pull out the cross symbol, which is a time symbol. This cross this, cross this. Okay, so 3 copies. And so let's just define this. This is the set of all triples, say A, B, C, such that A, B, and C are positive integers. Okay, great. So now that we've got those 2 sets defined, so we've got to find a one-to-one function mapping this set of triples to the positive integers. So we need it to be one-to-one. So in fact, there are many of these possible maps. So many such maps exist. I'll put one-to-one. Many such one-to-one maps exist, and so in particular, comes to mind is the fundamental theorem of arithmetic, okay? So what we can do is take primes to respective powers and define that as the map. So we'll define f of the triple A, B, C equal to 2 to the power of A. So 2 to the power of A times 3 to the power of B times 5 to the power of C. Okay, and because of the fundamental theorem of arithmetic, you could basically choose any 3 primes and define such a map. Okay, so now let's show that this map is one-to-one. Okay, so to show one-to-one, assume f of ABC. Now we're really talking about the point, right? So assume that this point is, or the map of this point is the same as the map of another point, and let's just pick, how about P, Q, and R? Or maybe even C, D, E, or sorry, D, E, F, something like that, just some different letters. Okay, and I can see that I've got P and Q in memory. I'll try not to run this as code. All right, so if we have this, then we put that into our definition and say then what we have is that 2 to the power of this times 3 to the power of B times 5 to the power of C is equal to the same thing, but if we have a P and a Q and an R there for f of P, Q, R. Okay, and now by the fundamental theorem of arithmetic, I hope I got that right. That is the fundamental theorem of arithmetic, right? That we have unique factorization. So that's what I mean here. So we must have the same exponent. So I'm just going to write by unique factorization. We must have A equal to P, B equal to Q, and C equal to R. All right, and then we've got to make the conclusion. Oh no, I've done it again. Yeah, it's doing its Wolfram alpha thing again. Okay, so then we make the conclusion that the points are the same. A, B, C is equal to P, Q, R. Hence, the points are the same. So this function is one-to-one. Okay, and let's turn this into a comment. Great. All right, so I'll just do one more here because we're basically out of time. So we've got 2 sets, right? The set between -1 and 1, and B is the set from 3 to 7. Prove that they have the same cardinality. So what you want to do is show that there exists a function f sending A to B that is a bijection, right? Because if you find a bijection between the sets, then they have the same cardinality. All right, so now if you look at these, they're just intervals, right? And there's nothing special about them. So you want to think of some simple one-to-one function. So choose a linear function, right? So linear functions are one-to-one. Okay, so put f of x, just an example. It doesn't have to be a linear function, but it'll make an easy example. So ax plus b, okay? And what we want is the endpoints to go to the endpoints. So this function f of x, which is linear, will be a bijection, provided we get the endpoints to match up. So what we want then is f of -1 equals 3, which is the endpoint of a b on the left, and we want f of 1 to be equal to 7. Okay, and now we just solve this. And then you could go into more detail and show that this is a bijection after you get the map, right? So the first one says that, let's see, -a, because because we're subbing in -1 into this. So minus a plus b is equal to 3. And the second one says a plus b is equal to 7, which is the other endpoint. And now so we can add the two equations. So we'll say adding. Then on the left we have 2b and the a's vanish. So 2b is equal to 3 plus 7, which is 10. So dividing by 2, b is equal to 5. And then a is equal to 7 minus the b, which is 5, and that's 2. Okay, so we get our map that f of x is equal to 2x plus 5. All right, and then we say this is a bijection, and then you've got to show that it's 1-to-1. Show that f is 1-to-1 and onto. All right, so I'll leave that as an exercise to you. Now there's a last question here, which is a little bit tricky. So I won't do this because we're pretty much out of time here. But you've got to show that the set of functions from a set x to the set 0, 1 has the same cardinality as the power set of x for all sets x. All right, so that's a bit of a tricky one, but the key here is basically to find a bijection. Okay, so what you want to do here then is to define g of f to be equal to the set of all x in x such that f of x is equal to 1. For example, all right, and then you can notice that this is actually a subset of x. So it does map to the power set. Okay, and then you've got to show that G is a bijection. All right, so that's all I have for you for now. So we have a break coming up. It's week 8, and then we have a break. So I guess I'll see you guys after the break. I hope you have an excellent break. Get some much needed rest, and maybe you have some travel plans. So enjoy yourselves, and I'll see you then. All right. Thank you, guys.